In this section, we're going to talk about the derivative in the tangent line problem. So we're going to revisit that problem that we introduced in section 1.1, which is where we are interested in finding a straight line tangent to a curve at a given point. So one thing that's important to note about this image right here is that we have a circle, we have a tangent line, and the line intersects the circle. In this case, it's a circle, only at the point P. That's the only place where it intersects that line. And there is, for any specific point P on the circle, there's one tangent line corresponding to that point. Now, if you don't have a circle, if you have a more interesting shape, it can take several of these forms. In this case, the tangent line is a horizontal line. In this case, the line actually goes through the curve. That will happen sometimes with tangent lines. That's the only way to intersect that point in only one's, or that equation in only the point P. In this case, technically, it does intersect the line down here, but when we worry about tangent lines, we're only looking at a certain area around the point. So this would technically be the tangent line to P through that curve. That's the only way you can do it. Now, as we said before, to find the equation of a straight line, we know that we need a point on the line and we need the slope of the line. So the point's easy, we're given P. The slope is actually the interesting question. And we know that we can approximate the slope at point P by drawing a secant line through P and another point Q on the graph as shown here. So if we pick this to be our P down here, and we pick this to be our Q, where we've just increased x by delta x and then plugged that into the function. This would be the line that we'd be talking about here. That's a secant line. And so let's go ahead and plug in some of our or label some of our variables. We've got P as the point C, F of C. This would be our x1, y1. We've got Q as the point C plus some change in x, F evaluated at that. So remember, delta x is just the change in x from P to Q, and that'll be x2, y2 when we go to find the slope. Now, finding the slope, we're just going to use the standard slope formula. It would be the rise, y2 minus y1 over x2 minus x1. So the rise over the run. In this case, that's f of c plus delta x minus f of c, okay? And that's going to be divided by c plus delta x minus c, because those are my two x values. So because that c plus delta x is in the argument or in the input of f, we can't do anything to that. We can't separate it out, so it has to stay as is. But in the denominator, we can cancel the c's. So this is f of c plus delta x minus f of c divided by delta x. Now, some people do like to use a c, or to use an h instead of delta x. So if you're more comfortable, you may use f of c plus h minus f of c divided by h if you want to. Nothing wrong with that. Okay, so you've probably seen an expression very similar to this before, maybe in this form. This is actually what we call the difference quotient, if you learn this in pre-cal. It's the difference quotient. And again, delta x is going to represent the change in x, and that f of c plus delta x minus f of c represents the change in y, so you may see that called delta y in some cases. Now, the closer your second point Q is to the original point P, the better your approximation will be. We illustrated that in section 1.1. So if P and Q are getting closer and closer and closer together, then the distance between them is getting smaller, so that means our delta x here, or if you call it h, is going to be approaching 0. So what that means is, if we want to find the exact slope of the tangent line through the point P, all we have to do is take the limit as delta x approaches 0 of the difference quotient. So this is actually the definition of a tangent line with slope m. If f is defined on an open interval containing c, and if the limit as delta x approaches 0 of the difference quotient here, f of c plus delta x minus f of c divided by delta x equals m, and if this limit exists, then the line passing through c f of c with a slope m is the tangent line. And if you want to use the h version, which most students tend to prefer this, it would look like this. The limit as h approaches 0 of f of c plus h minus f of c divided by h. Now, one thing that is very important to remember, this is very, very important, f of c plus h is not equal to f of c plus h. It's not equal to f of c plus f of h. There's nothing you can do to separate that. You have to actually plug in c plus h into the equation. Okay, another thing that is important to note is that the slope of the tangent line to the graph of f at that point is also called just the slope of the graph of f. So if anybody ever asks you to find the slope of the graph at a given point, all you have to do is find the slope of the tangent line. So let's look at a really, really simple example of how you would do this. Now, this is a linear function, f of x equals 3x plus 2, so hopefully you can look at this and tell that the slope is 3. We're just going to use it to illustrate the method for doing this. So, we're looking for the slope of the tangent line at c equals 2. Okay, so let's just pretend that we're going to plug this in. So m would be the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h. And remember, we're not going to drop our limit notation until we've plugged everything in. So in that case, that's going to be f of 2 plus h would be 3 times 2 plus h plus 2. And f of 2 would be 3 times 2 plus 2. And that's all divided by h. So that gives me the limit as h approaches 0 of, let's see, we'll have 6 plus 3h plus 2 minus 6 plus 2 all over h. That's the limit as h approaches 0 of, let's see, we've got 8 plus 3h minus 8. So the h's, sorry, the 8's cancel. So we have the limit as h approaches 0 of 3h over h. So this is the limit as h approaches 0 of 3. Now that we would go to plug that in, but there's nothing to plug into, the answer is just 3. So that's how it works in a very simple example. Now your goal in this process should always be to have the h on the bottom cancel out. So something should happen where you can factor out an h and have it cancel. Now we're going to look at an example that's a little bit more interesting. We've got f of x equals x squared minus 1. This is nonlinear. And we want to find the slope of the tangent line at the points 1, 0, and 3, 8. Now, I could do this twice using each value of c, or I could do it once and not have to reinvent the wheel. So I'm going to do that. I'm going to find the limit as h approaches 0 of f of c plus h minus f of c divided by h, and then I'm going to plug in each of my values of c. So this would be the limit as h approaches 0, f of c plus h is going to be c plus h squared minus 1. I just replace the x with c plus h. And then f of c is c squared minus 1, and that's all over h. So doing the algebra here, that gives me c squared plus 2ch plus h squared minus 1, and I'm going to distribute the negative, so that's minus c squared plus 1, all divided by h. C squareds go away, 1's go away. So I have the limit as h approaches 0 of 2ch plus h squared divided by h. And again, hopefully we'll be able to cancel out that h. So I can factor it out. That leaves me with 2c plus h. So I end up with the limit as h approaches 0 of 2c plus h, and now that I've actually got something that I can plug in h equals 0, I would have, let's see, that's going to be 2c plus 0. I can drop the notation, so this gives me 2c. Now, what we have found is a formula for the slope of the tangent line at x equals c. So all we have to do is figure out what our c is and then plug it in for each of the points that we want to find the tangent line for, or the slope of the tangent line for. So at the point 1, 0, that would mean that c is equal to 1, it's just the x value. So m would be 2 times 1, or 2. And at 3, 8, c would be equal to 3. So m would be 2 times 3, or 6. So you can see that the slope is not necessarily the same at every point. In fact, it'll usually be different. One special case that you may encounter is the following. If f is continuous at c and the limit is delta x approaches 0 of f of c plus delta x minus f of c divided by delta x is plus or minus infinity, then x equals c is actually going to be a vertical tangent line. So anytime you take your limit and you get plus or minus infinity, then x equals c is going to be a vertical tangent line. So the slope would be undefined in this case.